Welcome to another podcast from Peaceful Rooster Experience.
Yeah.
We've gotten a ton of research requests on data encoding.
Oh, yeah.
Yeah, so today we're going to do a deep dive into how it works
Okay.
and especially why it matters as technology changes.
Absolutely. It's a really fascinating area. And you're right, the evolution of it all, that's key. It's not just like how we store information now, but how we make sure that like systems can still talk to each other, Even when like how we encode data changes.
Right, yeah. So I know you've been digging into this. You've been looking at data structures and how those choices impact encoding. Like, to start off, why is the way that data is organized in memory so different from how it's stored, say, on your hard drive?
And think of it this way. In your computer's memory, data is arranged for speed, right?
Okay.
It's all about quick access. But on a hard drive, it's more like you're packing a suitcase efficiently. We call this whole process encoding.
Okay.
It's transforming data into a format that's suitable for storage or transmission.
So it's kind of like in memory, we have the luxury of being messy, but when we need to like send it out, we got to get organized.
Exactly. In memory, we can use things like pointers, which are like direct links between different pieces of data.
Right.
But when we encode it for storage or sending it over a network, those pointers don't work anymore.
Okay.
Everything has to be self-contained.
Okay. So that's where those byte sequences come in that I saw in your notes.
Yes.
It's like taking something apart, labeling all the pieces, and then packing it flat.
Precisely. And the way we label things, that's where encoding formats come in. Now, some programming languages, they have their own kind of built-in ways of doing this.
Well, that seems like it could cause problems, right?
Uh-huh.
If like every language is doing it a different way, it's like everyone's speaking a different dialect.
You hit the nail on the head. These language-specific formats can be a real pain if you're trying to share data between different systems.
Okay.
Plus, they often aren't really designed with security or efficiency in mind as like top priorities.
So that's where these more universal formats come in,
Yeah.
like JSON and XML.
Mm-hmm.
I know those at least by name.
Yes. Those are like the lingua franca of data exchange.
Yeah.
Human readable, which is great for developers, and widely supported across different systems.
But I've also seen in the research that they can be a little verbose,
Ah,
especially if you're working with, massive amounts of data.
that's true. That's particularly important when you think about, media streaming and things like that.
Yeah.
Like sending a huge image file using JSON or XML would be like sending a novel when you could just send a postcard with the same information.
So that's where binary formats step in.
Exactly. They are way more compact. They're efficient, especially for things like images and audio. It's all about representing the same information, but using fewer bits.
Okay.
So faster transmission and less storage space.
So it's like shorthand versus writing everything out longhand.
Perfect analogy. And then building on that, we have even more specialized binary formats like thrift and protocol buffers.
These sound like they're taking things to the next level.
They are. They're not just about encoding the data itself, but also about defining a strict schema for it. It's like a blueprint that says exactly what data is included and how it's organized.
So it's not just packing the suitcase, you're also including this really detailed inventory of what's inside.
Yes. And this brings a few big advantages, right?
Okay.
First, it makes things super efficient because you don't need to waste space on extra labels or formatting. Second, it helps with error checking because you can easily validate if the data actually matches the schema.
So it's like having a quality control check built right in. I bet that comes in handy with complex systems.
Absolutely. And this schema idea actually leads to a really interesting concept: code generation.
Okay.
With thrift and protocol buffers, you can actually generate code in different programming languages based on that schema.
Interesting.
Less manual work and less chance for errors when different systems need to talk to each other.
Okay, that's cool. But I've also come across this format called Avro. It seems to be doing things a bit differently. What's the deal with that?
Avro is really interesting because it takes a much more dynamic approach.
Okay.
Unlike those other formats where the schema is like baked right into the data, Avro separates the two.
Okay.
So this means the schema can evolve more easily over time.
It's like having an adaptable suitcase where you can like change the compartments as needed.
You got it. This makes Avro ideal for situations where the structure of the data might change a lot,
Okay.
like in evolving databases or, with streaming data.
Now you keep mentioning schemas, and it seems like they're really at the heart of all this.
They are. Think of a schema as a contract between systems.
Right.
It's a way to make sure everyone is speaking the same language when it comes to data.
And I'm guessing this is especially important when you're dealing with those compatibility issues.
You're absolutely right. Schemas are crucial for making sure that old and new systems can still exchange data, even if their encoding formats have changed over time.
This has been really helpful so far, going from those basic concepts to some of this like more advanced stuff. But I know data doesn't just sit still, right?
Yeah.
It's constantly moving between databases, services, all these different systems.
Exactly. And each of those scenarios, it has its own unique challenges when it comes to encoding and compatibility. That's what we'll dig into next.
Yeah, you're absolutely right about data being constantly on the move.
Right.
Let's start with databases.
Okay.
They're kind of central to so many applications, right?
Yeah, I've always thought of databases like these giant libraries with all that data just neatly organized on the shelves.
That's a great way to visualize it.
Mm.
And just like a library needs a cataloging system, databases rely on encoding to structure and store the data efficiently.
Makes sense. But databases are always changing, right? New data is coming in, old data is getting updated. How do we make sure those changes don't break things?
That's where backward compatibility comes in.
Okay. When you update the way data is encoded in a database, you have to make sure that any existing applications that rely on that data can still read it.
So you can't just go changing the format willy-nilly.
Exactly. Any changes to the encoding schema, they need to be carefully considered, right?
Right.
To make sure those older systems aren't left in the dust.
But it's not just about the old systems, right? What about new applications that might need to access older data?
That's the flip side of the coin. Forward compatibility.
Okay.
New applications should be able to understand data that was encoded using those older schemas.
Right.
This allows for seamless integration, right? Without having to rewrite a ton of legacy code.
So it's like ensuring all the books in the library, regardless of their age, can still be read.
Precisely. And achieving the smooth transition, it requires careful planning, right?
Uh-huh.
And choosing encoding formats that actually support what we call schema evolution.
Okay. That makes sense for databases.
Mm-hmm.
But what about when data needs to travel between different services? I imagine that gets even trickier.
It does. When we talk about services communicating, we're often in the realm of web services, right?
Okay.
Which use protocols like HTTP to exchange data over a network.
Ah, so this is where I've seen terms like REST and RPC come into play.
You're on the right track.
Okay.
REST, or representational state transfer, that's a popular approach that emphasizes simplicity and flexibility.
Okay, I've heard of like REST APIs. Are those related?
Definitely. REST APIs use standard HTTP methods like get, post, put, and delete to interact with data, which is treated as a resource with a unique URL.
Okay.
So it's like using a common language, HTTP, to request and send data between these services.
Right.
And because REST relies on these standard web protocols, it's relatively easy to connect different systems, even if they're built using different technologies.
That makes sense. But I've also seen RPC mentioned alongside REST. How does that differ?
RPC stands for Remote Procedure Call. It's a more direct approach where you're essentially calling a function on a remote server as if it were part of your local application.
Interesting. So it's like extending the capabilities of your application
Yeah.
by tapping into this remote functionality.
You got it. RPC can be very efficient, but it does require more upfront agreement on how the data is encoded because you're directly interacting with a specific function on that remote server.
Right. You need to make sure both sides are speaking the same language.
Exactly. So choosing the right encoding format is key in RPC to ensure that compatibility between the client making the call and the server responding.
Okay, so we've covered databases, we've talked about services.
Yeah.
What about message passing systems? Where do they fit in?
Message passing systems. They're like the postal service of the digital world.
Okay.
They allow applications to communicate indirectly by sending messages through what's called a message broker.
So instead of these direct calls, applications are dropping messages into a queue and the broker handles the delivery.
Exactly. This decoupling, it makes the systems more flexible and resilient because they don't need to be directly connected or aware of each other's inner workings.
But how do we make sure that those messages are understood, especially if the sender and receiver are using different versions of an encoding schema?
That's where our discussion of encoding formats and schema evolution comes full circle.
Okay.
Whether it's databases, services, or message queues, ensuring that smooth and reliable data flow, it requires really careful consideration of these factors.
It seems like choosing the right encoding format and planning for how that data structure might evolve are just crucial no matter what.
Absolutely. And that brings us to the broader importance of these schemas, which we'll dig into more deeply next.
Yeah, it really is amazing how those seemingly simple choices about how we represent data they end up having these huge ripple effects across entire systems.
It's like this chain reaction.
Right.
And schemas seem to be the key link holding it all together.
They really are. They provide that common language, that blueprint that everyone can agree on. And that's crucial for a few reasons.
Okay, break it down for me. Why are schemas so important? Well, first, think about documentation. A schema acts as this clear, concise record of how the data is organized, right? That's incredibly helpful for anyone working with that data, especially developers who need to understand how different systems interact.
So it's like a data dictionary, making sure everyone's on the same page.
Exactly. But schemas go beyond just documentation, right?
Okay.
They're also really important for error checking.
How so?
By defining the expected structure and the data types for a piece of data, a schema allows systems to validate incoming information and flag any inconsistencies or errors. This helps prevent, bad data from spreading through the system.
It's like having this quality control checkpoint for data, making sure everything meets the standards.
Precisely. And perhaps most importantly, schemas are the foundation for schema evolution, which we've talked a bit about.
Right, we've touched on backward and forward compatibility, but remind me one more time why schema evolution is so critical.
Because data requirements, they're constantly changing, right?
Right.
Think about a database for like an online store. As that business grows, they might need to add new fields for customer information. They might need to adjust existing fields or even remove fields that are no longer relevant.
So it's like renovating a house. You need to make changes without bringing the whole structure down.
That's a great analogy. Schema evolution allows us to make these changes in a really controlled way, minimizing disruption to those existing systems. It's all about finding that balance between, adapting to those new needs while also maintaining compatibility with the past.
Right. Those two tricky concepts again.
Yep.
Break it down for me one last time. What's the difference between backward and forward compatibility?
Think of it this way. Backward compatibility ensures that older systems can still understand data that's encoded using newer schemas. It's like making sure your old DVD player can still play the latest movies.
And forward compatibility?
Forward compatibility means that newer systems can understand data that was encoded using older schemas. It's like making sure your brand new Blu-ray player can still play those classic DVDs that you've collected over the years.
Okay, so backward compatibility is about keeping the past in the loop, while forward compatibility is about making sure the future can still access the past.
Exactly. And it's this delicate dance between the two that makes schema evolution such a critical aspect of data encoding.
This deep dive has been really eye-opening. We've uncovered this whole hidden world of complexity behind something we often take for granted.
It is amazing how much thought and ingenuity goes into making sure that our digital world runs smoothly, even as technology is rapidly evolving.
From these simple concepts like pointers and byte sequences to the intricacies of schema evolution and compatibility, it's clear that data encoding really plays a fundamental role in shaping our digital lives.
And as technology continues to advance, the challenges and the opportunities in this field, they're only going to get more and more exciting.
It really makes you wonder what new encoding formats, what new schema evolution strategies will emerge in the years to come.
What new languages will data learn to speak?
Yeah.
How will we ensure compatibility across this ever-expanding ecosystem of devices and systems?
Those are questions to ponder for sure. And we hope this deep dive has given you a new appreciation for this intricate world of data encoding and all those brilliant minds working behind the scenes to keep our digital world running smoothly. Thanks for joining us on this journey, and until next time, keep exploring.